So friends, today we are going to discuss a numerical problem which is based on the shear force and the bending moment diagram. Suppose this is the simply supported beam which is subjected to two concentrated movement of magnitude 7m and m acting at the point B and C. We have to find out the shear force and the bending moment diagram. So first step is always to find out the reaction at these supports. Suppose the reaction at the point D is acting vertically upward, okay, denoted by RD, and the reaction at the point A is acting vertically upward, denoted by RA. Now we know that RD, that is the sum of these two reactions, RA plus RD, RA plus RD is equal to the net load acting over this simply supported beam in vertical direction. So in vertical direction there is no load acting over this beam, so the sum of these two reactions is equal to 0. Now we know that at the hinge the summation of all the moments is equal to 0. So at point A, the hinge, the sum of all the moments is equal to 0. Now because of this reaction RD, there will be a moment of magnitude RD into this distance L plus L plus L, that is 3L, acting in anti-clockwise direction about this point, okay, and because of this concentrated movement there will be a moment of magnitude 7m acting in anti-clockwise direction about the point A. Why? Because this movement is of magnitude 7m is trying to rotate this beam element AC in anti-clockwise direction about the point A. That's why it is taken here as positive. Anti-clockwise is taken positive here. And this movement of magnitude m is trying to rotate this beam element AB in clockwise direction about the point A, as shown here. I am showing here to show you clarity. This is the point A, suppose, and this is the point B, okay, drawn directly below this point, and this movement is acting like this movement m. So it is trying to rotate this beam element AB in this direction, that is clockwise direction, with respect to this point A, that is about this point A. That's why it is taken as clockwise rotation. So I will put here as minus m clockwise and substitute it equal to 0. Okay, now solving this, what will we get? We will get RD is equal to how much? Minus 2m by L. Okay, and RA can be obtained from this equation by putting the value of RD here. So we can obtain RA as how much? 2m by L. Now friends, the value of RD is coming out to be negative, so the direction of RD is opposite to that was assumed by us in the previous time. So we will draw RD in vertically downward direction. So the magnitude of RD is how much? Minus 2m by L, and the magnitude of RA is 2m by L. Okay. Now friends, we will draw the shear force diagram by obtaining the shear force at the point A, B, C and D. So friends, we will find out the shear force at the point A, B, C and D. We will find out the shear force at the point A on the left side of the point A and on the right side of the point A. Why? Because there is a reaction RA of magnitude 2m by L is acting at the point A. That's why shear force will change suddenly when going from left side of the point A to the right side of the point A. That's why we have to calculate on both sides of the point A. Similarly, we have to calculate the shear force on the left side of the point D and on the right side of the point D, because there is a reaction acting in vertically downward direction at this point D, denoted by RD. That's why shear force will change when going from left side of the point D to the right side of the point D. And at point B and C there is no vertical load or point load acting. That's why we have to calculate directly shear force at the point B and C, denoted by SPB and this term. Okay, now we will calculate the shear force on the left side of the point A. For that, what we have to do, we have to draw a section on the left side of the point A, and this is the section XX drawn here. Now we know that according to the definition of the shear force, that shear force at a section is the sum of all the forces either on the left side of this section or on the right side of the section. So you can choose any side. I am choosing here the left side. So on the left side of this section, there is no force lying. That's why shear force on the left side of this section is 0. Now I will go on the right side of the point A and find out the shear force on the right side of the point A by drawing a section on the right side of the point A as drawn here. Now friends, at this section, the value of shear force is because of this reaction RA, which is acting at this point A. I am rubbing this and showing RA here. Okay, this is the RA acting at the point A, having the magnitude this much. So because of this force, there will be a shear force at this section of magnitude 2MYL. So 2MYL is written here like this, and it will have a positive sign. Why it is having positive sign? Because it is trying to rotate the beam element which is lying between the point A and this section XX, this beam element, in clockwise direction with respect to this point which is lying on this section XX. So that's why it is treated here as positive according to our sign convention shown here on the right side. Okay, so that's why I have taken here as positive. Now I want to determine the shear force at the point B. For that, I have to rub this section XX and again follow the same procedure to find out shear force at the point B. I have to draw a section here like this passing through the point B. Now looking on the left side of this section, you can see that only this force is contributing toward the shear force at this section XX. That's why the shear force at the point B will also be equal to plus 2M/L. And according to this sign convention, the shear force is positive. Now we will find out the shear force at the point C. So at the point C, if you draw a section like this to find out the shear force, now on the left side of this section, this force is only contributing toward the shear force. This movement will not contribute toward the shear force because concentrated movement does not contribute anything toward the shear force. That's why the shear force at this section will again be equal to plus 2M/L, that is equal to this RA, which is equal to 2M/L. So written here, and the sign will be positive according to this sign convention shown here. For more information on sign convention, you can watch my video lectures. You have to refer to my channel for that, so you can do that. Now friends, I want to determine the shear force on the left side of this point D. Okay, this term I have to determine. For that, I have to again follow the same procedure. That is, I have to draw a section like this here, XX. Now on the left side of this section, I can see that only this force is contributing toward the shear force. That's why I will write it again here, 2M/L. The magnitude of this force RA is 2M/L, so I have written here 2M/L, and these two movements will not contribute toward any shear force about this section XX. And the positive sign is taken because using this sign convention, and I have already told you in the this case the sign convention of how I have taken. And for more information, you can visit my channel and the video on sign convention. Now friends, on the right side of the point D, if you want to determine the shear force, then you have to draw a section on the right side of the point D. Now friends, see this. On the right side of this section, on the left side of this section, this force is contributing toward a shear force of magnitude this much, and this force is also contributing toward a shear force because this is lying at the point D. This force is passing through the point D. That's why because of this reaction, there will be a shear force of magnitude 2M/L, and because of this shear force, there will be a shear force of magnitude minus 2M/L. Why minus is taken here? See this friends. If this is our section XX, I am generating this portion of the beam here. This is the section XX suppose, and this was our point D lying here, and this was reaction RD going vertically downward. And this is the imaginary beam element which is lying between the point D and this section XX. Then this force RD is rotating this beam element in counterclockwise direction, which is taken as negative about this point in counterclockwise direction. So that's why it is taken as negative. So it will give us 0. Now I will draw the shear force diagram. Now at the point A, shear force is 0. So marking here 0. At the right side of the point A, the shear force is increasing to 2 MYL. So 2 MYL suppose lie here. 2 MYL, and shear force at the point B is plus 2 MYL. Okay, that is lying in same level of 2 MYL. And shear force at the point C is also 2 MYL, lying in the same level of 2 MYL. And shear force at the point D on the left side is 2 MYL, again lying in the same level, and it is going to 0 on the right side of the point D. So last cross will be here. So joining first point with the second, second with the third, third with the fourth, fourth with the fifth, and fifth with the sixth, we will get our shear force diagram. Okay friends, the point joining the point, the line joining the point A, B, C and D is a straight horizontal line because there is no load, vertical load lying between the point A and D. Okay friends. Now friends, we will find out the bending moments at the point A, B, C and D. We have to find out the bending moment at the point A directly because there is no concentrated moment lying here. But we have to find out the bending moment on the left side of this point B and on the right side of this point B. Also on the left side of this point C and on the right side of this point B. Why? Because there is a concentrated movement acting at these 2 points. And at the point D, we will find out the bending moment directly. So we will first calculate the bending moment at the point A. For that we have to follow the same procedure. That is, we have to construct a section here. The section XX here is constructed. And we know that bending moment is defined at a section as the algebraic sum of all the moments either on the left side of this section or on the right side of this section. So I am choosing the left side of this section. So on the left side of this section, you can see there is no movement or forces acting. Beam terminates after this point. That's why bending moment at the point A is 0. And the bending moment at the point B we want to determine, then we have to calculate the bending moment on the left side of the point B and on the right side of the point B. So bending moment on the left side of the point B we want to calculate, then we have to construct a section on the left side of the point B and look for the various forces which are contributing toward the bending moment on the left side of this point, on the left side of this section. So only this force is contributing towards the bending moment at this section XX. And it is creating a sagging bending movement here, which is positive. Why? Because this force is trying to rotate this beam element AB about B in this direction. So it is creating a concavity up like this. This is concavity up. The point A will move here to A dash, become A dash, and this beam will bend like this in concavity up direction. That's why it is treated as positive, and concavity down is treated as negative. That we will see later, but here it is positive. So it will create a bending moment of magnitude 2m by L, that is this force, into this distance L between A and B. So it will create a bending moment of 2m. Now I am roughing this. We will find out the bending moment on the right side of the point B, denoted by this term. So for that we have to again follow the same procedure. We have to draw a section on the right side of the point B. So this is the section X is drawn here. Now because of this force, there will be a bending moment about this section XX having the magnitude 2m by L, that is magnitude of this force into this distance L into L. Actually this section is lying very close to this point B, but for clarity I have shown it with some distance from the point B, so that if it is lying very close to B, that's why this distance between point A and this section XX can be treated as L, that is the distance between A and B is equivalent to the distance between A and this section XX. It is treated. Now it will give us this term, and because of this movement there will be this movement of magnitude plus m. Why? I will show you. According to our sign convention of concentrated movement, if a movement is acting on the left hand side of a section and going in clockwise direction, it is treated as positive. So similarly, this movement is acting in the left side of this section XX and is going in clockwise direction. That's why it is treated as positive. So it will give us 3m. Now we will calculate bending moment on the left side of the point C. For that, we have to again follow the same procedure. We have to draw a section on the left side of this point C. Okay, now C on the left side of this section. You can see that only this force and this concentrated movement is contributing toward the bending moment about this section XX. Okay, I am rubbing this 7m and writing here because it is creating a little bit confusion in your mind. Okay, it is acting at the point C, this 7m. Now, because of this force, there will be a moment of magnitude 2m by L into this distance L plus L 2L. And because of this concentrated movement, there will be a movement of plus m using this sign convention, and it will give us 5m. Now, we will calculate the bending moment on the right side of the point C. For that, we have to again follow the same procedure, that is drawing a section on the right side of the point C. Now, we can see that this force is lying on the left side of this section, will contribute toward a bending moment of how much? 2m by L into this distance L plus L, that is 2L, plus this is contributing toward a bending moment of m using this sign convention, and this is contributing toward a bending moment of minus 7m using this sign convention. Why? Because if this is the section XX and this movement is lying on the left side of this section and going in anti-clockwise direction, that's why it is treated as positive. Similar is the case here. This movement is lying on the left side of this section. This 7m is lying on the left side of this section. It is creating a little bit confusion in your mind, so I am drawing it little bit at some distance from this point C. So you can see now, this movement is lying on the left side of this section XX and is going in anti-clockwise direction like this. So it is treated as negative here. So this will give us bend movement as minus 2m. So I will write here as minus 2m. This will give us this much value of movement. Now I will find out the bending moment at D. For that, what we have to do? We have to again draw a section at the point D because we have to find out the bending moment at D. So this is the section XX drawn here. Now, because of this force, there will be a movement of how much? 2m by L into this distance L plus L plus L, that is 3L. So using this sign convention, it is creating sagging bending moment about this section XX, so treated as positive, and this movement will contribute toward plus m using this sign convention, and this movement will contribute toward minus 7m using this sign convention, and it will give us 0. Okay friends, now I will draw the bending moment diagram. So these lines are extended here and we are drawing these lines, that is joining these lines with this line. Now this is the point A, this is the point B, this is the point C, and this is the point D. Now friends, see this. At the point A, bending moment is 0, so making a cross here. On the left side of the point B, the bending moment is 2m, so writing it 2m here. Suppose 2m lie here above the point B. This is the 2m point, and on the right side of the point B, the bending moment is 3m, so it is increasing to 3m. Suppose 3m lie here above the point B, and on the left side of the point C, it is going to plus 5m, so it is again increasing to plus 5m. So I am rubbing this C, increasing to somewhere here. 5m will lie here above the point C, and it is going to minus 2m on the right side of the point C. So it is decreasing to minus 2m, that is going below this line. But all the bending moment lying below this line are treated as negative, so I will go here as minus 2m below the point C, and it is going to 0 at the point D. So making cross here at this line. So joining first point with the second, second with the third, third with the fourth, fourth with the fifth, okay, and fifth with the sixth, we will get our bending moment diagram. Also, these lines are inclined lines because the shape of shear force diagram between point A and B is a horizontal line. That's why the shape of bending moment diagram is an inclined line between point A and B. Similar is true for lines between point B and C and C and D. So this was all for today's topic, friends, and if you like my video, you can subscribe my channel and also press the bell icon for the notification.